In this problem, we're looking at two similar problems. It says the triangle ABC here in triangle XYZ are similar, and that means that they are exactly the same in every way, except that they might be blown up bigger or shrunk smaller. And then it's going to ask us some questions so that we can understand this better. It says complete the three pairs of proportions below. So ratio of lengths of the sides of triangle ABC. So if we're just looking at triangle ABC, it says side AB over side AC is what? And so what we have is AB over AC is 6 over 9, or we could reduce that to be 2 over 3. And we can write that in here, 2 over 3. And then it says, just below that, it's maybe just as easy to talk about these up and down a little bit. So the ratio of the lengths of sides of triangle XYZ that correspond to the sides of triangle ABC in the ratio above. So if I was looking at AB over AC, and then I wanted to come over here to this second triangle, I would say XY over XZ. So AB over AC is similar to XY over XZ. And that's what they're asking right here, XY over XZ. But what you can also see is that we have XY is 12 over XZ is 18. And if I simplify that, I could divide each of those by 6, and I would end up with 2 over 3. So that's another demonstration of them being similar. So then, if I want to come over here and look at AB over BC, so again, we're looking at AB, and then we're looking at BC. AB over BC is going to be 6 over 13, and we can't reduce that, so we'll just put that in here, 6 over 13. And then looking down again at the problem just below it, if I'm trying to make comparison to the other triangle, AB over BC is the same thing as XY over, let's see, YZ. I'm just X, Y over YZ. Trying to say the letters in the same order that I said them in the first thing. If we look at the numbers that go with this, XY is 12 and YZ is 26. We can divide each of those by 2 and get 6 over 13, which would be the same ratio. Okay, so that's XY. And in the last one, it's kind of given for us. We have AC over BC, so here's AC over BC, and AC over BC is 9 over 13. It gives us that. And then that is the same on the other triangle as XZ over YZ, XZ over YZ, and then we could look at the numbers that go with that, which is 12 over 26, XZ over YZ, whoops, I said it wrong, it's 18 over 26, and if I simplify that, I can divide each of those by 2, and I'm going to end up with 9 over 13, and put that in here also. So lots of similar things we could discover there, and we could even go back and notice that when we put this and this on top, we put this and this on top, and that was the same. And then when we put BC on the bottom twice, we put XC on the bottom twice here. So lots of similar things going on. If we read the statements in part B here, only one of them is actually true. It says, in each pair of proportion, the lengths of the sides of triangle ABC are in the same ratio as the lengths of the sides of triangle XYZ. That's true, but it is not a coincidence. Here, we're actually going to say it the right way. The lengths of the sides of triangle XYZ, this is because we compared the sides of triangle XYZ that correspond to the sides of ABC, and they are similar. Yes. And then it gets a little weirder here. In each pair of proportions, the lengths of the sides of triangle ABC are not in the same ratio as the lengths of the sides of triangle XYZ. That's not true, and it doesn't have anything to do with them being right triangles. In each pair of proportions, the lengths of the sides of triangles ABC are not in the same ratio. Well, yes, they are, as the lengths of sides of XYZ, and this is always true for similar triangles. Well, similar triangles, yes, if we took out the word not, then that would be true. Anyway, there's your right answer, and hopefully that kind of makes sense. It's kind of pleasing when you have similar triangles, set up all kinds of ratios of matching sides, kind of like a little logic thing. We can say AC is to XZ. We can say AB is to XY. We can say BC is to YZ. And the numbers all work out in these cool ratios.